Alright, in order to find the gain from the first stage, we need to figure out how much the second stage loads the first stage. In other words, we need to find the input resistance, Ri2, from the second stage that will be in parallel with Ro1. And to do so, we know what the DC current through Q17 is, so we can find what the equivalent resistance looking into the base of Q17 is. This resistance will be in parallel with R9, and then we can find the resistance looking into the base of Q16, which will be our Ri2. So REQ1 is equal to R pi 17 plus beta n plus 1 times R8, the resistance in the emitter of Q17. And this equals 36.9 kiloohms. This resistance is in parallel with R9 and is the emitter resistance for Q16. So we can say that Ri2 is equal to R pi 16 plus beta n plus 1 times the quantity R9 in parallel with REQ1. And when we substitute values, we find that this is 5.72 megaohms. Now, recalling that the output resistance from the first stage was 6.8 megaohms, we can figure out what the gain of our first stage is. So we'll say AV1 is equal to V1 divided by V input differential, where V1 is the voltage across the parallel resistors here. And this is equal to GM1 times RO1 in parallel with RI2, which equals 565, or in dB, 55 dB. Alright, so now we need to figure out what the gain from the next stage is. So going to the next stage, we need to find an equivalent input resistance, which we just found. We have a GM2 to find, a VI2, RO2, and we find the gain of that second stage. So here we see that Q16 forms a common collector amplifier, or a emitter follower. So Q16 is an emitter follower, which we know is just a voltage buffer that has a gain equal to 1, or approximately equal to 1. And the GM looking into that stage now is from this device. So we find GM2 is equal to GM17 divided by 1 plus GM17 times R8. Substituting values in that we already know, this is 6.8 millisiemens. Now, to find the output resistance, we need to find R up and R down, and they will be in parallel. R down is equal to RO17 times 1 plus GM17 times R8. R up is equal to RO13B, and the total resistance, RO2, is equal to R up in parallel with R down, and substituting values in would yield 80.9 kiloohms. Okay, so now we go to our output stage. Okay, so we're going to assume that RL here is equal to 2 kiloohms and that Q14 is supplying the current to it. In other words, the signal swing is up here, so we turn Q14 on and supply current to Q14. So we could draw an equivalent circuit for this. We are looking for the equivalent input resistance, Vx over Ix. So RO18 and RO19 are the resistances due to those diodes. And so we could find an equivalent resistance looking into the base of Q14, and then an equivalent resistance looking into the diode connected transistors Q18 and Q19. Okay, so we'll label this resistor REQ4, or this resistance REQ4, and this one REQ3. So looking into the base of Q14, we find that we have R pi 14 plus beta n plus 1 times the load resistance, which is equal to 505 kiloohms. Then combining this resistance with these other resistances here, we would get a 1 over GM18 plus 1 over GM19 plus an RO13A in parallel with REQ4. Now we can neglect 1 over GM resistances since they're probably small, and we would find that this is approximately equal to 177 kiloohms. Alright, so at this point we now know the total resistance seen by the emitter of Q23A, so we can find the input resistance of stage 3, which is equal to Vx over Ix here. So Ri3 is equal to R pi 23 plus a beta p plus 1 times REQ3. And substituting values in, we find that this is 9.04 mega ohms. From this, we can now figure out how much stage 3 loads stage 2 and find the total voltage gain. So AV2 is equal to big GM2 times RO2 in parallel with RI3, and is equal to 544.2, which is equal to 54.7 dB. The total voltage gain is just AV1 times AV2, which is equal to 109.8 dB. And now we need to find the output resistance. What we'll notice is we have 2 more gain stages, but both of the gain stages that we have left have unity gain values, and so they don't contribute to the overall voltage gain of the circuit. So to find the output resistance, we're going to note that we have a 27 ohm resistor that's going to be in series with the equivalent resistance that we see looking into Q14, which we'll label REQ5. So we'll put our test voltage source into the circuit. measure the current flowing through that voltage source, and we can find the output resistance of our 741 op amp. So here we see that REQ5 is equal to approximately 1 over GM14, which is 21 ohms, and this is in series with that 27 ohm resistor, so our R out is equal to 48 ohms for the 741 op amp. So we can make a small signal equivalent circuit similar to what we did for the two-stage operational amplifier that is as follows. Now we know the values for all of these components, and we know that the voltage gain for this circuit is AV is equal to 109.8 dB. The input resistance differentially is equal to 2.72 mega ohms, and the output resistance is equal to 48 ohms. Now you recall that for a voltage amplifier we want an infinite input resistance and a zero output resistance and an infinite voltage gain. Well, we don't achieve any of those things, but what we do see is we have very large voltage gain, very large input resistance, and a very small output resistance. So we can make a model for our 741 where we include these values. So here we have our inverting and non-inverting terminals. Here we have a voltage-dependent voltage source, VDVS. So this is our voltage gain. And we have an output resistance. So this is R out, this is R in differential, and we have our nice, good voltage amplifier. Alright, so that's how we do the analysis for the 741. And you can do similar analysis for almost any operational amplifier. We start with the DC bias, and then we do the small signal analysis. And the only difference in doing these complex amplifiers is recognizing which transistors are acting as DC biases and which transistors are acting as small signal gains.